You're watching a Channel 98 NBISD TV production.
Hey out there in TV land, welcome to that geometry show. I am your groovy host, Kevin Corpy, and I'm glad you joined me for another fantastic episode. Today we're going to be talking about a special quadrilateral called a trapezoid. Now the name itself invokes curiosity and wonder, so I hope you stick around and learn something. But before we start the lesson, I encourage you to all log on to the district's website, www.newbraunfels.txed.net, and download these worksheets I'm going to be using today. Work along with me at home. I spent a lot of time preparing them, and it's silly for me just to use them when they're right there for you as well. All right, lesson 17 is, of course, on trapezoids, and it's going to correspond with chapter 6.5 in your textbook. Okay, now a trapezoid is a special quadrilateral. We've been looking at special quadrilaterals in previous episodes. Last week we looked at parallelograms, and we even got more specific and looked at squares, triangles, and rhombi, or squares, rectangles, and rhombi, excuse me. Today we're going to back it up from parallelograms, and we're going to look at just a quadrilateral. A quadrilateral, remember, means a four-sided polygon. So here's what a trapezoid is, the formal definition. A trapezoid is a quadrilateral, four sides, with exactly one pair of parallel sides. So here's a trapezoid down here. Let's talk a little bit about the anatomy of this trapezoid. Okay, one pair of parallel sides, not two, exactly one. So this side here and this side here are the parallel sides, and we call those guys the bases. Okay, so the bases are the two parallel sides. Now we have these two opposite sides that are not parallel to each other, and we call those the legs. So the bases are the parallel sides, denoted by these arrows, and the legs are the non-parallel sides. Well, if you remember when we were talking about triangles, and especially isosceles triangles, where we also had something we call the base, we had base angles. A trapezoid has two sets of base angles. The ones for this base, angle P and angle A. I'm going to put two different tick marks because they aren't necessarily congruent. These are called base angles. And then we also have another set formed by this base up here with the two legs, angle T, which I'll put a triple arc on it, and angle R, 1, 2, 3, 4 arcs. Look at that. So we have four separate angles, making two pairs of base angles in a trapezoid. Now we can have other types of trapezoids that don't look like this. Sometimes you may see a trapezoid like this that almost looks kind of like a rectangle, but one of the sides has to violate being parallel to the other. So this side would be parallel to this one. And this is an interesting trapezoid because we have a right angle here. But the reason that it still is a trapezoid is because this side here and this side are not parallel to each other. Now here's a quick question. Would a square also be a trapezoid? Definitely has one pair of parallel sides, but because of this little word right here in the definition of a trapezoid can have only one, exactly one pair of parallel sides, and a square, as you remember, has two pairs. So a square, unfortunately, is many things, but a trapezoid, it is not. Now, as you can imagine, there are some special properties of trapezoids, and the first thing we want to look at is a special type of trapezoid. If the two legs of the trapezoid, remember the two legs are the non-parallel sides, if they happen to be congruent, the same length, then we say that the trapezoid is an isosceles trapezoid. And we spell that I-S-O-S-E-L-E-S. That's a cool word right there. So it's very similar to an isosceles triangle. And in fact, you can imagine this being a triangle. If I extended this up and made a peak, it's kind of like an isosceles triangle with the top lopped off. Okay, so we get this trapezoid. Now the legs are congruent, so we can put these tick marks denoting that they are congruent. All right, now if we have an isosceles trapezoid, parallel sides being the bases, two congruent legs, four base angles, we can look at the pairs of the base angles now having special properties. And in this trapezoid that's isosceles, the pairs of the base angles are in fact congruent to each other. So we could say angle P and angle A are the same measure. We'll say angle P is congruent to angle A, and we also have the other pair up top, angle T and angle R, and they are also congruent to each other. So we can write that as angle T is congruent to angle R. And remember the notation here, just to review, the angles are congruent because we say their measures are equal. Okay, so that's just kind of a notational review. Now that wasn't the case, remember, in this first one. We had 4 separate angles, and it wasn't necessarily isosceles, so the angles still form base pairs, but they weren't congruent. Well, there's another exciting, relatively exciting, property of an isosceles trapezoid, and that is that its diagonals are also congruent, which means they're the same length. Now, to construct the diagonals, all we have to do is connect opposite vertices. So if I could connect segment P or vertex P to R with a handy-dandy straight edge, like a ruler, I get segment PR, and I'll write that down here, segment PR. Remember, the segment itself has the bar above it, and the other diagonal would be segment AT or TA. And I can connect that, again, with the straight edge, and I get that diagonal. Okay, so PR, we say, is congruent to segment AT, and a notation, again, that means that their measures, PR is equal to AT. Without the bar, remember, it means the length of the segments. They have the exact same length. Okay, special properties, that's for an isosceles trapezoid. So now we have some anatomy figured out, and we have some special properties. It's time to look at some examples. And of course, what is an example if it doesn't have a little bit of algebra in it, and this one does? All right, let's read carefully. The measures of a pair of base angles in an isosceles trapezoid. That little word right there is very important. They're 7x minus 12 and 5x plus 6. We want to find the value of x. Well, where's our trapezoid? It's not given. So if it's not given, what do? We draw one. Now we're going to draw an isosceles trapezoid. A real conventional isosceles trapezoid would be to draw the base on the bottom to be a little bit longer, and that's kind of something that we have a natural tendency to do so that it looks more stable. We could easily have drawn it upside down like that. Okay? But we're going to use this one, and it says that the base angles are 7x, the pair of base angles are 7x minus 12 and 5x plus 6. So are we going to call them these the pair, these obtuse angles up here, or are they the acute angles? We don't really know, and it's not really important in this aspect so long as we do realize, if I'm calling it the bases down here, that this would be the other angle, 5x plus 6, and not to call these the angles that we're talking about. So the pairs are always associated by their common base. Now in an isosceles trapezoid, we just talked about the property that the two measures were equal. So I can create an algebraic expression. So I can say that 7x minus 12 is equal to 5x plus 6. And now I have a little algebraic equation. I can collect my x's on the left. So 7 minus 5 gives me 2 x's. And adding 12, I get 12 plus 6 is 18. Dividing both sides by 2, I get x equals 9. And if there were units involved here, I would put 9 units, such as 9 inches. But there weren't. Now, again, did we answer the question? This said to actually find the value of x. So we did answer the question, but if you have time, it would probably be beneficial to plug them back into each expression and make sure they are, in fact, the same. So let's try that. This angle here was 7 times x, which is 9, plus, minus 12, minus 12. So 7 times 9 is 63 minus 12, and that's 51 degrees. Okay, so if I plug it into the other expression, 5 times 9 plus 6, I should get the same answer. Let's keep our fingers crossed. 5 times 9 is 45 plus 6. 45 plus 6 is, look at that, 51 degrees. So that's a good check. We know we got the right answer. All right? And again, it doesn't really matter if it was these or these up here. But notice now after the fact, if this is 51, I did choose the correct angle because that's an acute angle, and this one up here appears to be obtuse, which is greater than 90. So if I had labeled it incorrectly, I could still find the correct measurements. The diagram is just important so that you can reference something. All right, another example. The measures of two base angles on the same side of the trapezoid. Okay, that's a little bit different. Are 10x plus 7 and 6x minus 3 respectively. What is the measure of the larger base angle? And there's a little hint here. The base angles in a trapezoid are formed by two parallel lines cut by a transversal. Wow. That's from a previous show. Let's go ahead and draw our trapezoid. Now notice it doesn't say that it's an isosceles trapezoid, so I'm going to draw a trapezoid that is not isosceles. And then these are going to be my parallel sides. and the angles on the same side. So we're not talking about a pair of base angles anymore. We're talking about maybe this one and this one. They have a common leg instead of a common base. Now, which one do I label 10x plus 7 and which one do I label 6x minus 3? Again, it's kind of irrelevant for trying to figure out what you need to do. And at the end, whichever angle was smaller or larger, we know that this one's going to be smaller because it appears to be acute and this one's obtuse. So I'm just going to go ahead and think that 10x minus 7, because 10 is larger and we're adding, might be larger. So I'm going to label this one as 10x plus 7 and this one as 6x minus 3. Now, we can't set those equal to each other because, first of all, it's not isosceles, and even if it were, these really have no special relationship that we talked about. So we need to go back to our parallel lines. If I extend the top base of this trapezoid and I extend the bottom base, they're parallel to each other, then this leg forms the transversal, remember? And we had special angles in this situation. We had alternate interior angles, we had alternate exterior angles, and the angles that we have here now are called the consecutive angles. And consecutive angles also had special properties. If you remember what they were, you're doing great, okay? I'll tell you what they were. Consecutive angles are supplementary. What does that mean? That means they add to 180 degrees. Now we have something we can work with. I can set the two expressions, add them together, and set it equal to 180. So I'll get 10x plus 7 plus 6x minus 3 has to equal 180. And once I get to my little algebraic expression, I can, I'm home free basically. I'm rounding third, coming in home. Let's collect my x's. 10 plus 6 is 16x. And 7 minus 3 is plus 4, and that equals 180. And so I subtract 4, and I get 16x equals 180 minus 4, which is 176. And I'm running out of room. So now I'll divide both sides by 16, and I get x equals 176 divided by 16. Well, if you can't figure out what that is, you can grab a calculator, punch it in very carefully, and you'll see that it's 11. Okay, now, did I answer the question? I found what x is. No, I didn't answer the question because in this case, it was asking for the measure of the larger base angle. So which expression is going to give the larger answer? Well, if you're not sure, we can plug it in and evaluate both of them. So the first angle would be the 10x plus 7, and I'm going to multiply now 10 times 11 plus 7, and 10 times 11 plus 7 comes out to 117 degrees. So that appears to be the obtuse one, and just to check, I'll plug it into the other one. The other one's 6x minus 3, so that's 6 times x minus 3. That's 66 minus 3, which is 63 degrees. And so definitely 117 is larger than 63. So answering the question is 117. And if I had mislabeled these, the expressions backwards, now I would know that the way that I've drawn it, I had them backwards and I can flip-flop them. Not a big deal. One more example here, and then I'm ready for a break. We're going to look at an isosceles trapezoid on the coordinate plane. Okay, and we're given 4 coordinates here of the vertices, and we want to find the measure of each diagonal. Well, the first thing we need to do is plot the points and see what we actually have. So my first vertex is negative 1, 5. So negative 1, 5 is up here. 2, 2 is going to be right in here. 0, negative 4 down yonder. And negative 7, positive 3 is in here. Now, this scale is very nice. It's gridded 11 units on the horizontal and 11 units on the vertical, so it preserves the squareness of the grid. So when I connect these vertices, I should actually have an isosceles trapezoid that appears to be so. So connecting the vertices with the straight edge to make it look pretty. Your teachers will like that if you make it look pretty. And the last vertex up here gives me that. So there's a nice little purple isosceles trapezoid. So can you identify the parallel sides? Well, the parallel sides are going to be this one here and this one here. And so this must be the congruent legs. Now, we want to find the measure of each diagonal. Remember, this is an isosceles trapezoid. And an isosceles trapezoid, the diagonals are congruent. So I could just find the measure of one of the diagonals, and that should be the measure of each of them. And it doesn't really matter which one I find. But I'm going to go ahead and draw it first. So I'm just going to choose to draw this one here. All right, and I'm going to find the measure of that diagonal. And what the heck, since I have the ruler right here, I'll go ahead and draw the other one. And now I can get a nice visual cue that they appear to be the same length. But for no rhyme or reason, I'm going to choose that point and this point. Okay? So finding the length, the diagonal, is the same as finding the distance between the points. And we've had the distance formula on a previous episode. The distance formula, remember, is basically a modified Pythagorean theorem. It's the square root of the change in x's squared plus the change in the y squared. And so my ordered pairs that I'm using, and the diagram helps me see which of the two to use, I'm using the point -1, 5, that one there, and the point 0, -4. So let's go ahead and plug it into the distance formula. The distance, which is actually the length, L, is going to be the square root of the change in the x's, so that's -1 minus 0 squared, plus the change in the y's, the corresponding y's, 5 minus -4 squared. And now I'll simplify under the radical. That's equal to the square root of -1 minus 0 is -1 squared, which is 1. 5 minus -4 is plus 9. 9 squared is 81. So I get the square root of 1 plus 81, which is the square root of 82. And that's a good place to stop unless you happen to have that handy-dandy calculator. Pull it out and punch it in, and you can see that it's approximately 9.055, ... It keeps on going. So that gives you an idea of what it is. Now that happened to be the length of this diagonal, but it's also the length of this diagonal. And you could verify if you had more time by doing the distance formula between these 2 points. But if it's an isosceles trapezoid, and I'm confident with my calculations, that should be the answer for both. All right, now it's time for a public service announcement, but don't go away, because when you get back, I might actually show you how to actually trap a zoid.
Alcohol kills more kids than all illegal drugs combined. Each day, 7,000 young people under the age of 16 have their first drink.
Twice as many kids use alcohol more than any illegal drug.
3 million kids ages 14 to 17 are considered regular drinkers.
Kids under the age of 21 will spend $5 billion on alcohol.
1 out of every 4 kids live in a home where alcohol is abused. Alcohol is a key factor in 1 out of 3 divorces. 1/2 of all adults have a family member who is an alcoholic.
It only takes one adult to make a difference.
It's not just about drinking and driving.
It's not about responsible underage drinking.
It is about not starting before the age of 21.
It's all about providing positive coping skills.
It's about weaving a web of support for each child.
Okay, welcome back. How to trap a zoid? I know that's why you came back. You can't actually trap a zoid. Zoids don't exist. You can trap a bear, but that's a different episode. Let's get back to the geometry. All right, talking about trapezoids, there is another special segment that might not be given to you that we can certainly draw, and it has a special name. It's called the median. And a median implies middle. Like if you're driving down the highway, the patch of grass in between the highways is called the median. It's the middle of the 2 highways. Middle is the same context here. Here's the formal definition, though. The median of a trapezoid, any trapezoid now, is the segment that joins the midpoints of the 2 legs. The legs are the non-parallel sides. Now, the median is a very important line segment, and we're going to talk about it in just a second, but what I want to do is actually show you what the median looks like. So here's the parallel sides, the bases, the 2 bases. You can call it B1 and B2, base 1, base 2 with the subscripts. These are the legs. Now to draw the median, I need to find the midpoint of this leg and the midpoint of that leg. And we can actually do that using a compass and a pencil. Okay, but that might be too involved for this show. So in class, depending on what your teacher wants, you might be able to just eyeball it. So from here to here, about halfway in between would be somewhere in there. And half the length of this diagonal might put me right in here. Okay, so again, that's an approximation. Now, if I connect those 2 dots with a straight line, again using my straight edge, I get that, and that looks pretty good. Here's the special property. This is, by the way, I'll label it the median. It has a special property. The median is always, not sometimes, it's always parallel to both of your bases. So what does that mean? That means that they will never intersect, that they have the exact same slope, and if the two bases are parallel to each other, we can use the arrow, then we can put the same exact arrow on the median. Okay, pretty cool. They all run the same direction. And as if that wasn't enough, the median has a special length related to the two bases, and here it is. The median length is always 1/2 of the sum of the two bases. Pretty cool. So here's what we can say. The median, the length of the median, or the measure of the median, is always going to be 1/2 the sum of the two bases. And I'm calling it B1 and B sub 2. So B sub 1 plus B sub 2. That's always going to be true. And notice that doesn't have to be for an isosceles trapezoid. That's for any trapezoid. So you'll have a lot of problems in class where you're given the lengths of 2 of the 3, and you have to find the third, the missing one. And that's not a big ordeal if you remember this formula. The median is half the length of the sum of the two bases. Okay, let's look at one of those types of examples. Here's what you might see in class or out in the real world somewhere. Given that segment VU is the median of a trapezoid, and let's identify VU, it's right here. Okay, so it's a median. So what does that mean? Before I even read on, I just want to say what that means in my own mind, but I'm going to speak out loud so you can hear me out there. That means that this segment is equal to that segment, which is good because they're both labeled as 10. And it also means that this segment is equal to this segment. And look, they're also both equal to 10. So not only are these equal to each other and these are equal to each other, but they're all 4 equal to each other. That would make this, although it doesn't say it, an isosceles trapezoid. Okay, that's nice to know. Now what we need to find here is the value of x. So notice this trapezoid, first of all, is inverted. We have the longer base on the top, which is not a big deal. This is the parallel side. This is the parallel side. So one base is 27. The other base is 15. And we have an algebraic expression for the median. So how are we going to find that x value? Well, we use that little property that we just learned, that the median is half the sum of the two bases. So let's go ahead and set up our expression. VU, the length of VU, is 1/2 the sum of the two bases. I'm going to use the letter notation here. That's going to be segment ZY plus segment WX. So it's always a nice idea to start off with this literal equation with just the variables here. And now we'll plug in what we know. VU is the variable expression 4x plus 5. And that's equal to 1/2. 1/2 is 1/2. It's a constant. The length of segment ZY is 27. Plus the length of segment WX is 15. So once again, I hit an algebraic expression. So it's not going to be very difficult if I know how to solve it. So I'm going to go ahead and leave the left side alone. And I'm going to add 27 and 15, and that gives me 1/2 of 42. Now, do I know what half of 42 is, or 42 divided by 2? It should be, it always was, and I think it still is, 21. Okay? So now you can tell we're making progress here. I'll subtract 5 from both sides. So 21 minus 5 is 16, and divide both sides by 4. I get x is equal to 4. How about that? So I have solved for x. Now bear in mind that I could have been given the variable expression for any one of the 3. It didn't have to be the median, but I would have to know the side lengths of the other 2, and we would just plug into this literal equation, and whichever one ended up being the unknown, it's just a little bit different in algebraic manipulation to solve for the unknown, but it's all using that same equation every single time. All right, now it's time for the part of the program we call the Say What? And I know you're saying what out there. What are we up to today? Well, we're going to look at a nice little application of trapezoids, and it deals with food, which I know is something that everyone is interested in. Okay? Food, food. You might have seen cafeteria trays before that were rectangular, but did you know that some cafeteria trays are shaped like isosceles trapezoids? Okay? Now, look at the diagram I have here. These are actually hexagons, but they are representing trapezoids. I couldn't find any picture of trapezoidal trays, but I know they exist. Actually, the food industry calls these trapezoids. So let me go ahead and draw it more like a trapezoid. Here's a food tray, and we've got some of them sitting around a table. One of them actually has food on it. And here's the other tray over here. Okay? So food goes on the trays. And why in the heck are they shaped like a trapezoid? Well, why wouldn't they be rectangle? It's a space-saving design. This is an improvement, and it allows the trapezoids to nicely fit around the table so that people aren't fighting for space. So it's a nice ergonomic design. So let's go ahead and take an example here. If the measures of one pair of base angles of a tray, a food tray, are 120 degrees, then what are the measures of the other pair of the base angles? All right, well, let's go ahead and draw our food tray here, like we're staring down at it. I'm going to draw mine in green. I always go for the green trays for some reason. And so we're staring right down at it. Now I'm not going to draw food on there because it's just going to clutter my diagram. Carefully, what do we have? One pair of base angles are 120 degrees. So it's either this one and this one, or this one and this one. Now 120 is an obtuse angle, so although it doesn't matter, I'm going to try and make it germane to the diagram. I'm going to call the obtuse angle 120. So that's 120, and this is 120. Okay? Now the question is asking us to find the measure of this. And I know that these are also going to be congruent because it's isosceles. Now we've already worked the problem very similar to this in an earlier part of the show. These by themselves in the trapezoid don't have any special property. But if I magically extend out the food tray, infringing upon my neighbor's food space, he'll have to forgive me, and I extend this out to create that transversal, now I know again that these two angles are consecutive interior angles, and we know they're supplementary. So I know that their sum has to add to 180. So let me just call this angle 1, and I'll call this angle 2. Okay? So I know that 120 degrees plus the measure of angle 1, since they're consecutive interior angles, has to equal 180 degrees. And boy, that's a real easy equation to solve. The measure of angle 1 equals 180 minus 120, and that equals 60 degrees. Well, since it's an isosceles trapezoid, that also equals the measure of angle 2, and believe it or not, we are done. So now we're hungry, we can go raid the fridge. Well, sadly, that concludes another episode of That Geometry Show. Hope you had a good time today. I heard you learned something new. Until next time, I'm Kevin Corpy, and I'll catch you on the flip side. Got to get away from that bear.